There exists a profound paradox between what Saturn's moon, Mimas, appears to be and what it actually contains beneath its ancient, frozen surface. When you examine the raw imagery transmitted back from deep space, this celestial body presents itself as the very embodiment of a lifeless world. The moon is uniformly gray, densely pockmarked with impact craters, and locked in permanent ice. Its surface reveals absolutely no indication of geological vitality, no fractures penetrating the crust, no volcanic vents spraying material into the void, and no evidence of tectonic movement reshaping the landscape. From a purely visual standpoint, Mimas has earned recognition for a single, striking characteristic: its eerie similarity to the fictional Death Star from popular culture. The moon's face is overwhelmingly dominated by the Herschel crater, an enormous impact basin that extends across roughly 1/3 of the entire visible hemisphere. This feature, which bears the name of William Herschel, the astronomer who first identified this moon in 1789, lends Mimas a peculiar, almost engineered appearance. The sight of it triggers an instinctive reaction in observers, suggesting something constructed rather than naturally formed, as though it were an ancient manufactured object abandoned in the darkness of space, or a fragment of cosmic wreckage locked in eternal orbit. This battered, seemingly inert exterior led generations of planetary scientists to classify Mimas as what they termed a geological fossil. The prevailing assumption held that this moon was essentially a monolithic chunk of water ice that had remained fundamentally unchanged for billions of years since the solar system's formation. This interpretation seemed entirely logical given the available evidence. When researchers searched for potentially habitable environments or reservoirs of liquid water in the outer solar system, they naturally directed their attention toward moons that displayed obvious signs of activity. Bodies like Enceladus and Europa, which visibly expel water and ice particles from their interiors into surrounding space, became the prime targets of scientific investigation. Mimas, by contrast, received virtually no consideration in these searches. Its appearance suggested a shell far too thick and a structure far too fractured to conceal anything scientifically valuable beneath its surface. The moon seemed to offer nothing more than a historical record of ancient bombardment, a cosmic punching bag that had absorbed impacts for eons without ever developing the internal dynamics necessary to support liquid water or, by extension, the potential for life. However, cutting-edge analysis of archival data has definitively established that this unremarkable exterior functions as an extraordinarily effective disguise. Recent computational work performed on measurements collected during the Cassini mission, led by planetary scientist Valery Laney and his research team, has conclusively demonstrated that Mimas is categorically not a solid block of frozen water extending from surface to core. Despite the weapon-like artificial appearance of its battered exterior shell, the interior of this moon maintains active processes. Most remarkably, this seemingly dead world conceals a global ocean of liquid water, located approximately 20 to 30 kilometers beneath its icy outer crust. While scientists initially explored alternative hypotheses to explain the observational data, current computational models consistently point toward a subsurface ocean as the explanation most compatible with all available measurements. This revelation fundamentally upends established frameworks for identifying potentially habitable worlds beyond Earth. We are not observing a frozen, inert boulder circling Saturn. We are examining a candidate for what might be termed a stealth ocean world, a body that has successfully masqueraded as worthless debris for the entire duration of human space exploration. The discovery forces a complete reevaluation of how we assess the habitability potential of distant moons and challenges the assumption that surface appearance provides reliable information about interior conditions. In 2010, the Cassini spacecraft executed a close approach to Mimas, designed to collect detailed measurements of surface temperatures across the moon's hemisphere. The scientific team conducting this observation had no expectation of encountering anything unusual during the data collection process. For an airless body like Mimas, lacking any atmosphere to redistribute thermal energy, scientists anticipated a straightforward and predictable pattern. Standard models predicted that surface temperatures would reach their maximum values near the equator during local noon, when the sun stood highest in the sky, and would decrease smoothly and gradually as measurements moved toward the polar regions or into areas experiencing nighttime conditions. The resulting temperature map should have displayed a gentle, continuous gradient of heat diminishing outward from the peak values. The data transmitted back to Earth by Cassini's composite infrared spectrometer revealed something entirely unexpected and scientifically puzzling. Rather than showing the predicted smooth thermal transition, the temperature map displayed sharp, high-contrast boundaries separating distinct thermal zones. The warmer region configured itself into a shape bearing an unmistakable resemblance to the 1980s arcade game character Pac-Man, complete with what appeared to be a mouth oriented toward the Herschel crater. This bizarre pattern initially baffled the mission scientists who first examined the thermal imagery, as nothing in their theoretical models had prepared them for such a geometrically defined temperature distribution. This thermal anomaly emerged because Mimas possesses a fundamentally non-uniform surface composition and texture. The Pac-Man shape represents dramatic variations in how different areas of the surface interact with solar radiation, the regions appearing yellow and red on the thermal maps, indicating higher temperatures, correspond to surface materials that retain absorbed heat effectively over extended periods. Conversely, the areas rendered in blue, showing lower temperatures, represent materials that release thermal energy almost instantaneously after the sun's rays cease to strike them directly. This property, which physicists call thermal inertia, determines how efficiently a material stores heat energy. Terrestrial experience provides useful analogies for understanding thermal inertia. On Earth, dense materials like concrete, asphalt, or solid rock remain noticeably warm for hours after sunset because these substances possess high thermal inertia and release their stored heat very slowly. Loose sand, however, exhibits low thermal inertia and cools rapidly the moment direct sunlight disappears. Mimas demonstrated what scientists describe as a split thermal personality. The leading hemisphere of the Moon, the face that perpetually points forward in the direction of orbital motion, behaves thermally, like solid, consolidated rock, maintaining elevated temperatures well after rotating away from direct sunlight. The trailing hemisphere and other protected regions behave more like fluffy, unconsolidated powder, shedding heat almost instantaneously as soon as solar radiation stops hitting the surface. The physical mechanism creating this stark textural division adds yet another layer to the Moon's peculiar nature. As Mimas follows its orbital path around Saturn, the leading face of the Moon continuously plows through a stream of high-energy electrons trapped within Saturn's powerful magnetosphere. These energetic particles relentlessly bombard the ice crystals covering the forward-facing hemisphere, fundamentally altering the surface structure. The electron bombardment effectively welds the initially powdery ice grains together, centering them into solid, consolidated blocks of ice through a process similar to what happens when loose snow is compressed into hard-packed ice. This sintering process substantially increases the surface's thermal inertia by creating better thermal contact between individual ice particles. The regions of Mimas that face away from the direction of orbital motion, shielded from the electron stream by the Moon's own bulk, escape this bombardment and retain their original powdery, unconsolidated structure. This creates a sharp boundary across the surface that remains completely invisible to optical imaging systems, but becomes glaringly apparent when viewed through thermal infrared sensors. The pattern reinforces the interpretation that Mimas represents a heavily weathered object that has endured not merely mechanical battering from asteroid impacts, but also continuous assault from the invisible radiation environment created by its parent planet. Prior to the discovery of the subsurface ocean, this bizarre thermal signature appeared to be simply another peculiarity that made Mimas seem like a frozen, battered relic from the solar system's violent early history, rather than a geologically dynamic body worthy of detailed investigation. The thermal pattern highlighted a surface that had been subjected to intense external forces, operating continuously for billions of years, effectively directing scientific attention away from consideration of what might exist in the deep interior beneath the bombarded crust. The Herschel crater constitutes the single most prominent feature visible on Mimas and serves as far more than merely a surface blemish. This enormous impact basin represents a physical archive of a catastrophic collision that very nearly obliterated the Moon entirely. The crater extends approximately 130 kilometers across its widest dimension. Mimas itself measures only about 400 kilometers in diameter at its equator. These dimensions mean that the Herschel crater dominates roughly 1/3 of the Moon's entire visible face, creating the distinctive appearance that has made Mimas famous among space enthusiasts. To fully appreciate the devastating violence of this impact, it helps to scale the event to Earth's dimensions. If a collision of proportionally similar magnitude struck our planet, The resulting impact crater would exceed the geographic area of the Australian continent. The energy released during this collision was so extraordinarily intense that the physical effects of the impact remain visible not just at the impact site itself, but across the entire globe of the moon. When the asteroid struck Mimas, it did far more than simply excavate a large hole in the surface ice. The collision generated massive seismic shock waves that propagated through the entire interior of the moon at high velocity. These pressure waves traveled through the moon's center and converged with extraordinary precision at a single point located on the exact opposite side of the moon from the impact site. Planetary scientists refer to this geometrically opposite location as the antipode. At this convergence point, the surface exhibits severe structural damage. The ground appears buckled and fractured into deep canyons and extensive fracture systems that planetary geologists classify as chasmata. This damage resulted entirely from the focused, amplified seismic energy from the Herschel impact traveling through the moon's interior and forcefully deforming the surface crust from below as the converging shock waves pushed upward. The structural evidence paints a picture of a world that sustained damage penetrating all the way through its interior. The Herschel crater itself displays immense scale in all dimensions. The crater walls rise approximately 5 kilometers above the surrounding terrain, creating a formidable rim that encircles the entire basin. The floor of the crater plunges roughly 10 kilometers below the average surface level, creating a depression so deep that if you stood on one rim, the opposite rim would lie beyond the horizon of this small world. At the geometric center of the crater floor, there rises a massive central peak that towers approximately 6 kilometers above the crater floor. This peak formed through a process called isostatic rebound, which occurred when the ground beneath the impact site, having been compressed to extreme depths by the collision, rebounded elastically and violently upward immediately after the impacting body had excavated the crater. This central peak structure has been preserved in nearly perfect condition because Mimas lacks any atmosphere that might drive erosion through wind, and it experiences no precipitation or temperature cycling that might gradually weather the sharp features over time. For several decades, this extensive impact damage actually supported the prevailing scientific hypothesis that Mimas consisted entirely of solid water ice, extending from the surface to the core. When seismic waves propagate through a liquid ocean, the fluid medium tends to dampen and disperse the wave energy because liquids absorb and redistribute mechanical energy very differently than solid materials do. The fact that shock waves from the Herschel impact traveled so efficiently through the moon, creating such severe antipodal damage, strongly suggested that Mimas existed in a completely frozen state, solid throughout its entire interior volume, at the time the collision occurred. This interpretation adds considerable complexity to the recent discovery of the current liquid ocean. The evidence indicates that Mimas most likely existed as a solid ice ball when the catastrophic Herschel impact occurred. The ocean that scientists have now detected appears to be a much more recent development, one that formed sometime after this near-fatal collision, rather than having existed throughout the moon's entire history. The Herschel crater left Mimas appearing as a battered, static shell, an impression that strongly reinforced the conclusion that this was a dead object drifting lifelessly through the vacuum of space. The discovery of the liquid ocean concealed within Mimas was not accomplished through visual inspection of surface photographs or through detection of thermal anomalies emanating from the interior. Instead, the ocean revealed its presence through extremely precise measurements of how the moon moves through space as it orbits Saturn. Astronomers utilized archival data collected by the Cassini spacecraft to track the rotation of Mimas with exceptional accuracy. They focused their analysis on specific, well-defined impact craters scattered across the surface, using these features as reference markers to measure the moon's rotational position over extended time periods. The goal was to determine whether Mimas maintained a perfectly steady rotation or whether subtle variations existed in its spin rate. The measurements revealed that Mimas does not rotate steadily. Instead, the moon exhibits a specific type of rotational behavior that physicists call libration. This phenomenon manifests as a subtle oscillation or wobble superimposed on the moon's overall rotation as it completes each orbit around Saturn. The libration occurs because Mimas follows a slightly elliptical rather than perfectly circular orbital path. This elliptical orbit means that the moon's orbital velocity changes continuously throughout each revolution. When Mimas approaches the closest point in its orbit to Saturn, called periapsis, it moves faster. When it reaches the most distant point, called apoapsis, it travels more slowly. These velocity changes cause the moon to rock gently back and forth around its rotation axis, creating the libration. Every moon that follows an elliptical orbit experiences libration to some degree. The amplitude of this wobbling motion is determined by the internal mass distribution and structural configuration of the body. When scientists calculated the expected libration amplitude for Mimas, they constructed their theoretical models, assuming the moon consisted of a homogeneous solid ball composed of ice and rock. Given Mimas's known total mass and physical dimensions, the laws of physics impose strict limits on how much wobbling a solid object can exhibit. Saturn's gravitational force acts on the entire mass of the moon, creating torques that keep the rotation relatively stable and damping out any tendency toward excessive wobbling. If Mimas were indeed solid throughout, the outer ice crust and the deeper rocky core would be rigidly connected. Under these conditions, the entire moon would necessarily move as a single integrated unit. Changing the rotational motion of such a rigidly connected object requires overcoming substantial resistance from the entire mass, which in turn requires considerable energy input. This mechanical resistance would keep the libration amplitude small and subtle, well below the detection threshold of all but the most sensitive measurement techniques. The observational data transmitted from Cassini revealed a libration amplitude that proved physically impossible to explain if Mimas were actually a solid object. The moon was oscillating back and forth with roughly twice the amplitude that theoretical models predicted for a solid body. This magnitude of motion clearly indicated that the outer ice shell was not rigidly attached to the deeper, denser core. The only viable explanation for such an unexpectedly large oscillation amplitude is that the icy outer crust has become physically decoupled from the interior. This decoupling creates a scenario where the outer shell possesses freedom to slide around independently of the underlying core, no longer constrained to move in perfect synchrony with the deep interior. For the ice shell to slide freely in this manner, it must be floating on some intermediate layer rather than sitting in direct contact with solid material below. Such sliding requires a lubricating layer that eliminates friction between the ice above and the rock below. In planetary science, only one substance can realistically exist in this lubricating layer under the temperature and pressure conditions expected inside Mimas: liquid water. No other material possesses the right combination of properties to explain the observation. This excessive libration provided what investigators describe as the smoking gun evidence. It definitively proved that the ice shell is mechanically decoupled from the rocky core, slipping and sliding over a global layer of liquid water. The wobble represents the physical signature of a hidden ocean that permits the surface to move with dramatically more freedom than would ever be possible for a solid moon. The confirmed existence of a liquid ocean inside Mimas immediately creates a significant challenge for planetary physics. Mimas is an extremely small celestial body by astronomical standards. In planetary science, fundamental thermodynamic principles dictate that small objects lose their internal heat very rapidly. Any thermal energy that remained trapped inside Mimas from the moon's initial formation, approximately 4.5 billion years ago, should have radiated away into the surrounding space billions of years in the past. According to all standard thermal evolution calculations, Mimas should long ago have become a completely cold, thermally dead object. For liquid water to continue existing in the present day, there must be an active, ongoing power source continuously generating sufficient heat to prevent the ocean from freezing solid. The source of this energy is Saturn's gravity operating through a mechanism called tidal heating. Mimas does not orbit Saturn along a perfectly circular path. Instead, its orbital trajectory is slightly elliptical, which astronomers quantify by stating that the orbit has measurable eccentricity. During each complete revolution around Saturn, this elliptical path causes Mimas to move closer to the planet and then drift farther away in a repeating cycle. This constant variation in orbital distance creates a dynamically changing gravitational environment that subjects the moon to varying levels of gravitational force. When Mimas reaches periapsis, the closest point in its orbit to Saturn, the planet's immense gravitational field pulls with maximum strength on the moon. This powerful gravitational attraction physically stretches and deforms Mimas into a slightly elongated, oblong shape aligned with the direction towards Saturn. When Mimas subsequently moves to apoapsis, the farthest point in its orbit, Saturn's gravitational pull diminishes substantially, and the moon relaxes back toward a more spherical shape. This cycle of deformation and relaxation repeats during every single orbit, subjecting the moon to continuous mechanical stress. This perpetual stretching and relaxing is termed tidal flexing. and it operates as a mechanical process, functionally equivalent to repeatedly bending a metal wire back and forth. If you take a wire and bend it at one point repeatedly, you'll notice that the metal at the bend location becomes noticeably hot after sufficient repetitions. This heating occurs due to internal friction between the atoms comprising the metal as they slide past one another during each bending cycle. The identical physical principle operates inside Mimas. The rock and ice composing the moon's interior grind against each other as the moon's shape continuously deforms and relaxes. This internal friction converts mechanical energy from the orbital motion into thermal energy, generating substantial amounts of heat deep within the moon's interior. Because this tidal heating is generated primarily in the deep interior where deformation is greatest, the thermal energy radiates outward from the rocky core toward the surface. As this heat flows upward through the overlying ice, it raises the temperature of the lowermost layers of the ice shell to the melting point of water. Over millions of years of continuous heating, this process has created a global reservoir of liquid water, trapped between the rocky core at the center and the solid ice crust forming the outer shell. What makes Mimas particularly unique is how efficiently it retains this tidally generated heat. On a moon like Enceladus, which experiences tidal heating of similar origin, the thermal energy is so intense and concentrated that it fractures the ice shell, creating fissures that vent heat and material directly into space through dramatic geysers. On Mimas, by contrast, the tidal heating operates more subtly. The heat generation is strong enough to maintain a liquid ocean by continuously melting ice from below, but not violent enough to fracture the thick outer ice shell and create pathways for heat to escape. The ice crust, estimated at approximately 30 kilometers thick, functions as an extraordinarily effective thermal insulation blanket. It traps virtually all the tidally generated heat inside the moon, allowing the subsurface ocean to persist indefinitely without producing any detectable thermal signature on the surface. This creates a perfectly sealed thermal system, continuously powered by Saturn's gravity, with essentially no external evidence of the internal activity. In the ongoing study of Saturn's moon system, Enceladus has consistently served as the archetypal example of an ocean world, the standard against which all other potentially habitable moons are measured. Enceladus functions effectively as the loud, attention-seeking neighbor in Saturn's family of satellites. It announces its presence and advertises its internal ocean in the most spectacular and unambiguous manner conceivable. Enceladus continuously shoots massive plumes of water, vapor, and tiny ice particles, hundreds of kilometers into the vacuum of space. From prominent fractures concentrated near its south pole, these geysers erupt with such tremendous force and such enormous volumes of material that the ejected particles actually supply one of Saturn's more tenuous rings with a steady stream of fresh ice. The E-ring, one of Saturn's most diffuse rings, consists almost entirely of ice particles originating from Enceladus's geysers. Because of these visually obvious eruptions, scientists understood that Enceladus harbored a subsurface ocean almost from the moment the Cassini spacecraft began its detailed observations of the Saturn system. The evidence was dramatic, visible, and scientifically indisputable. Mimas represents the exact opposite end of this spectrum of ocean world behavior. It qualifies as what might be termed a stealth ocean world, a body that successfully conceals all evidence of its internal liquid reservoir. Despite orbiting within the same planetary system as Enceladus and experiencing similar types of gravitational forcing from Saturn, Mimas keeps its secrets completely contained beneath an impenetrable shell. Mimas displays none of the tiger stripe fractures that characterize Enceladus's south polar region. It generates no fissures that vent water or heat into surrounding space. It does not resurface itself continuously with fresh deposits of ice particles, as Enceladus does, through the steady accumulation of material that falls back to the surface after being ejected by the geysers. Instead, Mimas maintains its heavily cratered, ancient-looking surface that appears completely and utterly dead to any form of visual inspection. The fundamental difference between these two ocean worlds lies primarily in the thickness of their respective ice shells, and how this thickness affects the ability of internal pressure to breach the surface. On Enceladus, particularly near the geologically active south polar region, the ice crust can be remarkably thin, perhaps as little as 1 to 5 kilometers in thickness. This represents a relatively thin barrier that internal pressure can overcome. The combination of tidal heating generating elevated temperatures and pressures in the subsurface ocean, combined with the structural weakness created by such a thin ice layer, allows the pressurized water to force its way through cracks and weak points in the crust, creating the spectacular plumes that make Enceladus famous. Mimas, however, possesses a far more substantial containment barrier. Scientific models indicate that the ice shell overlying Mimas's ocean measures between 20 and 30 kilometers in thickness. This represents a massive, extraordinarily heavy lid that effectively suppresses any tendency for internal activity to manifest at the surface. The pressure exerted by the liquid ocean against the underside of this ice shell, while substantial, proves insufficient to crack through such an enormous thickness of solid ice. The sheer mass of the overlying ice creates compressive forces that keep any incipient crack sealed and prevent the formation of through-going fractures that might allow material to escape. This dramatic difference in ice shell thickness provides a complete explanation for why Mimas successfully deceived astronomers for such an extended period. For decades, the scientific community operated under specific, well-established biases that guided the search for potentially habitable environments beyond Earth. Researchers actively looked for surface signals that would indicate internal activity. The implicit assumption held that if a moon contained a subsurface ocean, particularly one warm enough to potentially support life, that ocean would inevitably produce some visible evidence at the surface. Scientists searched for smooth resurfaced plains, indicating recent geological activity, for fractures suggesting internal stresses, or for active plumes demonstrating that pressurized material was escaping from the interior. Mimas exhibits precisely none of these expected indicators. Its surface remains ancient, heavily cratered, and apparently unchanged for billions of years. It has now been definitively proven that you can successfully hide a global ocean completely and effectively beneath a sufficiently thick ice shell overlying a battered, ancient-looking surface. This comparison between Enceladus and Mimas forces a fundamental reevaluation of how planetary scientists categorize and prioritize moons for detailed investigation. Enceladus, with its obvious geysers and clear surface activity, now appears likely to represent the exception rather than the rule in the population of ocean worlds. It is comparatively rare for a moon to experience tidal heating intense enough and focused enough to fracture its ice shell and shoot water visibly into space. It is almost certainly much more common for moons to resemble Mimas in their presentation, quietly harboring subsurface oceans beneath thick, intact ice shells that show no external evidence of the liquid water below. This realization suggests that there could potentially be dozens of these stealth ocean worlds scattered throughout our solar system, bodies that have been systematically dismissed as scientifically uninteresting simply because they appear to be nothing more than dead, frozen rocks when viewed from the outside. Mimas delivers a profound lesson about the limitations of visual assessment. It teaches us that the complete absence of surface geological activity cannot be taken as proof of a geologically or thermally dead interior. The lack of visible activity might simply mean that the thermal insulation provided by a thick ice shell is working with perfect efficiency, trapping all evidence of internal dynamics beneath an impenetrable barrier. Perhaps the most scientifically shocking aspect of the hidden ocean on Mimas is not merely the fact that it exists at all, but rather the evidence suggesting that this ocean is extraordinarily young in geological terms. Based on sophisticated computer models used to analyze the orbital mechanics and thermal evolution of the moon, scientists currently estimate that this subsurface ocean likely formed only about 15 million years ago. When placed in the context of a solar system that has existed for approximately 4.5 billion years, 15 million years represents an almost infinitesimally brief span of time. It suggests very strongly that we are observing a world that has only recently awakened from billions of years of dormancy. The primary evidence supporting this surprisingly young age comes from detailed examination of the current condition of surface features, particularly the major impact craters. Water ice, despite being solid at the temperatures found on Mimas's surface, does not behave like rock over extended geological timescales. Over periods of millions to billions of years, ice exhibits a property called viscous relaxation, where it flows extremely slowly like an extraordinarily viscous fluid. especially when warmed from below. This occurs because the molecular structure of ice allows the crystal lattice to deform gradually under stress, even at temperatures well below the melting point, though the process operates far more rapidly when the ice approaches melting temperatures. If Mimas had possessed a warm liquid interior radiating heat upward for billions of years, that sustained internal heating would have gradually softened the overlying ice shell from below over immense spans of geological time. The force of gravity acting on this softened, partially plastic ice would have naturally pulled down the high crater walls and caused the ice to flow into the deep crater basins, gradually filling them in. The surface would undergo continuous modification, with topographic relief slowly diminishing over time, until the surface appeared smooth, muted, and relatively featureless. Sharp crater rims would slump into gentle hills. Deep crater floors would fill in and rise. The overall appearance would be one of a relaxed, softened landscape where ancient scars had been partially erased by slow, viscous flow. That is categorically not what observers see when examining Mimas today. The Herschel crater remains remarkably sharp, jagged, and deep. Its towering walls still rise approximately 5 kilometers above the surrounding plains, and the crater floor still plunges roughly 10 kilometers below the average surface elevation. The central peak remains a dramatic, sharply defined feature, rising 6 kilometers above the crater floor. These structural elements could only survive in their current pristine state if the ice shell remained extremely cold, stiff, and mechanically rigid for virtually the entire history of the Moon following the impact that created Herschel crater. The excellent preservation of these violent impact scars provides strong evidence that the interior of Mimas was frozen completely solid when these major impacts occurred and remained in that frozen state for billions of years. Afterward, only recently, in geological terms, has the interior warmed sufficiently to generate a liquid ocean, and this ocean has not yet existed long enough for the heat it radiates upward to significantly soften the ice shell and trigger viscous relaxation of the surface features. The orbital dynamics of the Mimas-Saturn system provide additional supporting evidence for this timeline of recent ocean formation. The tidal heating mechanism that powers and maintains the ocean derives its energy from the orbital eccentricity of Mimas. The Moon's elliptical orbit subjects it to varying gravitational forces that generate the tidal flexing and internal friction that produces heat. However, this process does not continue indefinitely without consequences for the orbit itself. The tidal heating mechanism consumes orbital energy. As heat is generated inside the Moon through friction, that energy must come from somewhere, and it is extracted from the orbital motion itself. Over hundreds of millions of years, this continuous energy transfer typically has the effect of correcting and circularizing the orbit. The tidal forces act as a brake on the eccentricity, gradually damping the elliptical nature of the orbit and causing the path to evolve toward a perfect circle. Once the orbit becomes fully circular, the distance between the Moon and planet becomes constant. The varying gravitational forces disappear. Tidal flexing ceases, and the internal heat generation stops. The ocean would then gradually freeze solid again as residual heat radiates away into space with no mechanism to replace it. The fact that Mimas currently maintains a measurably eccentric orbit, one with sufficient ellipticity to drive ongoing tidal heating, strongly suggests that this orbital configuration is a relatively recent development. The system has not yet had sufficient time to consume the orbital eccentricity and circularize the path through the normal tidal evolution process. This observation is entirely consistent with the hypothesis that something gravitationally kicked Mimas into its current eccentric orbit only a few million years ago. This evidence collectively paints a fascinating picture of a solar system that continues to evolve and change in significant ways, even billions of years after its formation. Mimas evidently spent the vast majority of its existence, roughly 4.5 billion years, as a completely frozen, geologically dead block of ice and rock. Then, at some point in the relatively recent past, a gravitational interaction, perhaps involving orbital resonances with other moons or perturbations from passing objects, kicked the Moon into a new eccentric orbital path. This orbital change ignited the tidal heating engine for the first time, and ice that had remained frozen for eons began melting from the inside out as frictional heat accumulated in the interior. We are observing Mimas at an exceptionally rare and specific moment in its evolutionary life cycle. We are effectively witnessing the birth of an ocean world, catching it in the early stages of its transformation from a dead ice ball into a potentially habitable environment. The liquid water is likely still expanding its domain, slowly melting additional ice from the ceiling of the ocean cavity and increasing the total volume of liquid water present. But the ocean has not existed for a sufficient duration to erase or significantly modify the ancient impact history still clearly written on the surface. The reclassification of Mimas from a dead, frozen relic to an active ocean world represents one of the most significant paradigm shifts in planetary science over the last decade. It compels the scientific community to abandon the comfortable assumption that we can reliably judge the internal state and habitability potential of a celestial body by examining its exterior appearance. Throughout the entire history of space exploration, mission planners and scientists have prioritized exploration targets based primarily on evidence of surface activity. Funding, spacecraft missions, and scientific attention followed the geysers, the smooth, resurfaced areas, the visible cracks and fissures. The operating assumption held that if a world looked dead from orbit, it was dead all the way through. Mimas has conclusively proven that this methodology is fundamentally and dangerously flawed. A world can present the appearance of a frozen, heavily battered artifact left over from the violent early epochs of solar system formation, while simultaneously harboring all the necessary conditions for life just a few dozen kilometers beneath the surface dust and impact debris. The implications of this discovery reach far beyond the immediate scientific value of understanding one additional moon of Saturn. This discovery fundamentally breaks the traditional astronomical definition of the habitable zone, the region around a star where conditions are considered suitable for liquid water to exist on a planetary surface. For generations, students learned that liquid water requires a planet or moon to orbit within a specific range of distances from its parent star. The habitable zone concept, often called the Goldilocks zone, identified the region where temperatures are neither too hot nor too cold, where stellar radiation provides just the right amount of heating to maintain surface water in liquid form. Mimas provides definitive proof that gravitational interactions can be just as effective at creating and maintaining habitable environments as stellar radiation. It demonstrates beyond any doubt that a world can generate its own internal heat through purely mechanical processes, maintaining liquid water in the freezing darkness of the outer solar system solely through orbital dynamics and tidal forces, with essentially no contribution from solar heating. The moon orbits so far from the sun that solar radiation provides negligible warmth, yet its ocean persists indefinitely powered entirely by Saturn's gravity. This realization opens up the number of potentially habitable locations in the universe by several orders of magnitude. It means that the search for life need not focus exclusively on Earth-like planets orbiting within their star's habitable zone. Instead, any moon caught in a gravitational tug-of-war with its parent planet, subjected to tidal forces that generate internal heating, must now be considered a potential habitat. This dramatically expands the census of potentially habitable worlds, because small moons are extraordinarily abundant in planetary systems, far outnumbering the planets themselves. The implications extend far beyond Saturn's system. If Mimas can successfully hide a global ocean beneath an ancient, cratered surface, then scientists must systematically question everything previously assumed about other small, icy moons throughout the outer solar system that have been written off as scientifically uninteresting. Moons orbiting Uranus, such as Ariel or Miranda, or moons circling Neptune, such as Proteus, exist in similar physical environments. They are small, cold, distant from the sun, and they follow eccentric orbits that subject them to tidal forces. Until the Mimas discovery, these moons receive minimal scientific attention because they look solid, ancient, and dead when viewed through telescopes or during brief spacecraft flybys. Now, these objects must be reconsidered as prime candidates for harboring stealth oceans. The scientific community effectively has to return to the drawing board and recheck its work on dozens of objects that were previously categorized as mere space debris, geologically inert remnants of planetary formation, with no scientific value beyond recording ancient impact histories. Each of these objects must now be reevaluated with the understanding that a thick ice shell can completely hide an ocean that might have existed for millions or even billions of years. This paradigm shift fundamentally changes how space agencies and scientists design future planetary exploration missions. A simple camera-equipped flyby spacecraft, while useful for initial reconnaissance, is no longer sufficient to comprehensively survey a planetary system and identify all potentially habitable environments. Cameras can photograph the surface, spectrometers can analyze surface composition, but neither instrument can penetrate dozens of kilometers of ice to detect a hidden ocean, to find the truth about what lies beneath the surface. Space agencies need to commit resources to place spacecraft into long-term orbit around these candidate moons, where sensitive instruments can make the precise measurements necessary to detect subsurface oceans. The key measurements require detecting subtle variations in the moon's gravitational field and measuring tiny oscillations in rotational motion. Scientists need to feel the way the moon moves through space, rather than merely looking at its appearance. Gravity mapping can reveal mass concentrations and mass deficits that indicate the presence of liquid layers. Measurements of libration amplitude, like those that revealed Mimas's ocean, can detect the mechanical decoupling of the ice shell from the core that indicates a lubricating liquid layer. These measurements demand extended observation periods, careful trajectory planning, and sophisticated instruments, all of which require expensive, complex orbital missions rather than quick flybys. The Mimas discovery fundamentally alters our perception of the solar system's structure and the distribution of potentially habitable environments. Scientists used to look at our planetary system and perceive a few rare oases of potential habitability scattered amidst a vast desert of dead, frozen rock. Earth stood alone as the only confirmed world with surface liquid water. A handful of moons, most notably Europa and Enceladus, were suspected to harbor subsurface oceans based on clear surface evidence. Everything else appeared to be barren wasteland. The reality now appears likely to be dramatically different from this sparse picture. We are almost certainly looking at a solar system where liquid water is far more common than previously believed, but this water is simply hidden from casual view beneath thick shells of ice. The most battered, quiet, and visually unsuspecting objects scattered throughout the outer solar system may actually be the ones that are most geologically active and potentially most alive on the inside. The absence of surface activity may be the best camouflage an ocean world can possess. Mimas should not be regarded as an anomaly, an exceptional case that represents a rare coincidence of unusual circumstances. Instead, it likely serves as the prototype for an entirely new class of ocean worlds that scientists are only beginning to recognize and understand. This class of stealth ocean worlds may be the dominant type of habitable environment in our solar system, and perhaps throughout the galaxy. If small moons with subsurface oceans are common around gas giant planets, and if gas giant planets are abundant in planetary systems throughout the universe, then habitable environments may be extraordinarily common on a cosmic scale, hidden beneath innocent-looking surfaces that have caused them to be systematically overlooked for generations. The story of Mimas fundamentally transforms humanity's search for life beyond Earth. It teaches humility about the limitations of visual assessment and the dangers of dismissing objects based on surface appearance alone. It demonstrates that the universe can hide profound secrets in plain sight, that some of the most significant discoveries await, not at obviously interesting locations, but in the places we assumed were too mundane to warrant investigation. The moon that looks like a weapon, that appears artificial, that seems like nothing more than a frozen chunk of debris, may actually be one of the solar system's most remarkable laboratories for studying the conditions necessary for life. As space exploration continues and more sophisticated missions visit the outer solar system, Mimas will serve as a cautionary tale and an inspiration. It will remind scientists to question assumptions, to look deeper than surface features, and to recognize that habitability can hide beneath even the most unpromising exteriors. The solar system is likely filled with worlds like Mimas, quiet moons orbiting in the darkness, concealing liquid oceans beneath ancient ice, waiting patiently for humanity to develop the technology and insight necessary to discover what lies beneath.